to treat exponent as a binary number of bits. Okay, it will treat exponent as a binary number of bits. The first exponential. Okay, the main idea is to treat exponent as a binary number of bits. That means from x0 to x power n, x0 to xn minus 1. Okay, so for example, when you have the 128 number, okay, so when you have the exponent as a 128, so how we are calculating 128 means 1 0 0 7 zeros. Okay, 1 6 zeros. Okay, we will say that here. Okay, so for example, here we have 128. So 1 to a power 128 is the exponent value. Okay, so what you are doing means we are going to convert the exponent. Okay, we are going to convert the exponent as a binary number of bits. Okay, when you are converting the exponent as a binary number of bits, okay, so for example, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. Okay, so if it is a 128, we have 1 0 zeros. Okay, 1 6 zeros, right? Okay, so if it is a 128, if it is a different number, we have different values. Okay, 2 power values. Okay, after converting to binary number of bits, okay, then what you have to do means finally you have to include the intermediate results. Okay, for example, here the square value is 7, 2 power 7. 7 is the exponent value here. Okay, so there. Okay, so finally include the intermediate results to the final result wherever 1 is placed in the binary bits of the exponent. Okay, so finally you have to include the intermediate result to the final result wherever 1 is placed in the binary bits of the exponent. Okay, so that's what the first exponential we are doing. Okay, for example, we just receive the example. Okay, so it's used to simplify the calculation, model expansion calculations. Okay, for example, 5 power 128 mod 30. So this is what we have to find out the answer for the 5 power 128 mod 30. Okay, for that what we are going to do means using the model expansion. Okay, we are first taking the exponent value, we are converting it as a binary bits. Okay, we are converting as a binary bits. Okay, so once we calculate the binary bits, then we have to check where there is a 1. Okay, so we have to put the intermediate result in these places. Okay, so that we can get the final answer. Okay, so for that what we are doing means, so 2 power 0, 2 power 1, everything. Okay, so we are by calculating the value 5 2 power 0. Okay, 5 2 power 0 means what? 5 power 2 in bracket whole bracket 0. Okay, so that means 2 into 0, 2 power 0 will be 1. Okay, 2 power 0 will be 5. So 5 power 1 mod 13 result will be 5. Just a minute. Just okay. So in this first we have to calculate the values. Okay. So for each and every one we are calculating. Okay. So 5 2 power 0, 5 power 1, the result will be 5. So for next what we are doing 5 2 power 1. Okay. So next we are going to calculate the value for the 5 2 power 1. Okay, mod 30. So when you are calculating 5 2 power 1 will be 5 square. So 25 mod 13 result will be 2. Okay. Next what we have to calculate for the 2 power 2. Okay, 5 2 power 2. Okay. For that what we are doing means 5 2 power 2. Okay. So we already know the 5 square value. Okay, we already know the 5 square value. So what you are going to do means you are going to apply the result, this result into here. So we already know the 5 square value. What is the 5 square value? 12. So also 5 instead of 5 square, we are applying the 12. So the 12 square mod 13. So 144 mod 13 result will be 1. Okay. Next 5 to power 3. Okay. We can write this one in this form. 5 to power 2 whole 2. Okay. So that we already know the 5 to power 2 value. I mean 5 power 4 value. Okay. So that is a 1. So we are applying the 5 to power 2 result into here. Okay. So that will be 5 to instead of 5 to power 2, we are applying the result as 1. So 1 square mod 13 will be answer will be 1. Okay, so next 5 to power 4, we are applying this result into here. Next, we are applying the result into here. Next, we are applying this result into here. Next, we are applying this result into here. So that the calculation will be very simple. Okay, you need to calculate for large number of values. Okay, you need to calculate only for the small number of exponent values. Okay, so by applying the previous result into the next one, okay, so we are doing the operation for the small numbers. We are not doing operation for the large numbers. Finally, what you have to do for 5 or 128, we have to apply the intermediate result into wherever the 1 is placed. Okay, here 1 is placed on the 2 power 7. So 5 2 power 7, the value is 1. Okay, so 1 mod 13 result will be 1. Okay, so this is the final answer. So 5 or 128 mod 13, the result will be 1. Okay, so by applying the previous result to the next one, okay, so we can we can do the calculation for the small numbers. We don't need to do the calculation for the large numbers. Okay, for example, this one 8 power 3024 mod 11. Okay, 8 power 3024 mod 11. Okay, so when you are doing 8 power 3024 mod 11 using the calculator, okay, so you'll get the large values, large numbers. Okay, so instead of that, what you are doing means, okay, for 3024, we are converting into the binary bits. Okay, when you are converting to binary bits, you can get this one 1 0 1 1 1 1 0 1 0 0 0. Okay, so when you are converting the 3024 into binary bits, you can get this value. So 240, 241, 242, 243, 244, 245, 6, 7, 8, 9, 10, 11. Okay, next what you have to do means we are going to calculate the values for the 2 power 4, 2 power 6, 2 power 7, 2 power 8, 2 power 9, 2 power 11. Okay, we are going to calculate the value for the 2 power 4, 6, 7, 8, 9, 11. Okay, for that we are starting from the small digits. Okay, so that we can get apply the previous result here. So that we can get the our calculation will be very simple. Okay, so here 8 2 power 0, 8 2 power 0, 2 power 0 means 1, 8 power 1. 8 mod 11 will be 8. Okay, next 8 2 power 1, 8 square. Okay, so 8 square value will be 64 mod 11, answer will be 9. Next 8 2 power 2. So when you are going to 8 2 power 2, okay, so we are applying this previous result into here. 8 square values we already know 9. 8 square mod 11 is 9. So we are applying the 9 values here. So 9 square mod 11 result will be 4. Okay, next when you are going to calculate for 8 to power 3, that means 8 power 8. Okay, so we are applying the previous result into here. We already know 2 power 2, so 8 2 power 2 whole 2. So 4 into 2 8. Okay, so already know the 2 power 2 value 4. So 4 square mod 11, 16 mod 11 will be 5. Okay, so now we are applying the previous result into here. For this one, it will be applied here. So this one will be applied here. So this one will be applied here. So this one will be applied here. So this result will be applied here. So this result will be applied here. This result will be applied here. Okay. So in this way, we are simplifying the calculation. Okay. In the modular expansions, okay, we are simplifying the calculation. After find outing the values, okay. After find outing the value for 2 power 4, 2 power 6, 2 power 7, 2 power 8, 2 power 9, 2 power 11, we are applying all those values in the binary digits. Wherever one is placed, we are applying that. We are applying those values. Okay. For 8 to power 11, the value is 5. Okay. For 8 to power 9, okay, the value is 9. Okay. For 8 to power 8, the value is 3. For 8 to power 7, the value is 5. 8 to power 6, the value is 4. 8 to power 4, the value is 3. Mod 11. So when you are doing normal multiplication and taking the mod 11, you are getting the value as 4. If you want, you can also simplify this one also. Okay. For example, 5 into 9 mod 11, 5 into 4 mod 11, then 3 mod 11. Okay. So whatever the way you can simplify, you can even do the simplification. Okay. So finally, you get the result as 4. For 8 power 3024 mod 11, the value will be, remainder will be 4. Okay. The remainder will be 4. So this is what the modular expansion. So in the modular expansion, what you are doing means you are calculating the remainder when a positive integer a is raised to the xth power. Okay. So to simplifying the calculation, okay, instead of calculating the large numbers, okay, if the exponent will be converted to the binary digit, so that we are doing calculation for with the small numbers. Okay, we are doing the calculation with the small numbers, so I can get the result easily. Okay, so this is what the simplified way of the modular exponentials. Okay, any doubt in this? So that's a normal factorization. Okay, when you're doing the normal factorization, you can do that. So if I ask me now 2 power 0, okay. So when you're adding the 3024, that's it. 2 power 11, okay. 2 power 11 plus 2 power 9 plus 2 power 8 plus 2 power 7 plus 2 power 6. When you're adding this value, okay, so 2 power 11 value, okay. 2 power 11, 2 power 10, 2 power 9 plus 2 power 8 plus 2 power 7 2 power 10 2 power, okay, so this this one this one this one this one this one, okay. So when you are adding this value, you will get the 3024. Okay, so when you are adding this 2 power 11, 2 power 9, 2 power 8, 2 power 7, 2 power 6, 2 power 4, okay, or when you are doing the normal factorization, okay, 3024. So when you are doing the normal factorization, you get this value. Okay, so when you are getting 3024, so when you're doing normal factorization, you will get the values this one 101111 this one. Okay, for example, when you're getting the sum, you're getting the sum value, the remainder will be 0. Okay, then again when you are doing the factorization, okay, again you will get the remainder as 0. So again remainder will be 0. Again the remainder will be 0. Okay, so doing the factorization also you can get the this values. Okay, what? Okay, binary you can convert the 3024 into binary digits. Okay, are you clear, Karthik Magadevan? Karthik Magadevan, are you clear? Now, can you know how to convert the 3024 into binary bits? Okay, so in this way you can do that. Okay, after that, by doing this value, do this operation, we can simplify the exponent value. We can get the smaller exponent. So using the smaller exponent, we can calculate the remainder. Okay, so this is the model exponential. So, do anyone have doubt in the model exponential? Karthik Magadan, still they have doubt. Okay, so what? How we do 3024? So normally when you're, how do you do the factorization? Okay, so 15 2. Okay, so how you do, what you, how you are getting that 0. Okay, so again remainder will be 0. Again when you are doing this 7, okay, 5, what is remaining 6, right? 0. Okay, like that when you are getting, finally you get the answer as 1. So when you are adding this 1, okay, so when you are adding this 1 0 0 1 1 1 1 0 1 0. When you are doing this factorization, finally when you are, finally you get the remainder as 1. When you are adding all the remainders, you will get this value, entire 11 digits value. Okay, so this is what the model exponentials. Okay, so if you are find getting the problem 8 power 3 to model 11 using the model exponential, then you have to do this type only. Okay, if they're specifically saying model exponentials, you have to perform on this method. Okay, next one, Fermat's little theorem. Okay, next what you are going to is Fermat's little theorem. Okay, so when you are going to the Fermat's little theorem, okay, it is also known as Fermat's theorem is also known as Fermat's little theorem or and Fermat's probability test. Okay, the Fermat's theorem is also known as Fermat's little theorem and Fermat's probability test in number theory. Okay, the statement first given in 1640. Okay, the statement is first given in 1640 by French mathematician. Okay, by French mathematician Fermats, Ferrari de Fermats. Okay, but he presented this equation without any proof. Okay, in 1640s, the Fermats presented this equation without publishing any proof. Okay, he just stated that this is a theorem. But instead of that, the Euler's in 1743, okay, we already see the Euler's theorem, right? The Euler's presented this theorem with published proof on in 1743. Okay, so Fermat is presented this theorem without proof, and the Euler's presented the same theorem with a proof in 1743. Okay, so that we are saying we are calling it as a Euler's theorem. Okay, we are not specifying with the Fermat's theorem. We are always doing a problem with the Euler's theorem. Okay, so what he stated means the Fermat's. Okay, he stated that if P is a prime number, okay, if P is a prime number, then for any integer a, P is a prime number, then for any integer a, the number a power p minus a. Okay, a power p minus a is an integer multiple of p. Okay, in the number a power p minus a is an integer multiple of p. Okay, so it is expressed modular arithmetic. It's expressed as a power p congruent to a mod p. Okay, a power p congruent to a mod p. Okay. Okay, what's this statement? Any integer a, the number a power p minus a is an integer multiple of p. For example, we are taking a as a 2. Okay, we are taking a as a 2, p as a 7. Okay, then 2 power 7 is a 128. Okay, 2 power 7 is 128. So what is a power, the number a power p minus a is an integer multiple of p. Okay, so 128 minus 2. A power p is a 128. 128 minus 2 is 126. So 126 is a 7 into 18. So it is a multiple of 7. So 126 is a multiple of 7. Okay. So if a power p minus a is a 126 here. Okay. So it is a multiple of p. So what is the p value here? 7. Okay. So a power p minus a is a integer multiple of 7. So 7 into 18 is a 126. So that's what is stated here. Okay. So if p is a prime number, it's stated if p is a prime number, okay, then for any integer a, the number a power p minus a is an integer multiple of p. Okay, a power p minus a is an integer multiple of p. So that's what I'm saying. If a is a 2, p equal to 7, then a power p is a 128. A power p is a 128. What is the a value? 2. Okay, so it's a 126. So 126 is a multiple of p. What is a p here? 7. 126 is a multiple of 7. 7 into 18 is a 126. So always 120. I mean, always if it is a prime number, okay, then a power p minus a is a multiple of p. So that's what is stated here. We can also say another version of here. Okay, if a is not divisible by p. Okay, if a is not divisible by p or p is not divisible by a. Okay, if a is not divisible by p, Fermat's little theorem is equivalent to the statement that a power p minus 1 minus 1. Okay, a power p minus 1 is an integer multiple of p. Okay, a power p minus 1 is an integer multiple of p. This is the another version of Fermat's theorem. Okay, for example, again we take the same a and p. Okay, a equal to 2, p equal to 7. So when you are doing this, a is not divided by p. Okay, a is not divisible by p or p is not divisible by a. Okay, if it is that, then a power p minus 1, 2 power 7 minus 1 minus 1. So 2 power 7 minus 1 is 6. Okay, 2 power 6 minus 1. Okay, 2 power 6 is 64. Okay, 64 minus 1 is a 63. Okay, 2 power 6 is a 64. 64 minus 1 is a 63. Okay, that is a power p minus 1 minus 1. Okay, then it is a multiple of p. What is a p? P is a 7. 63 is a multiple of p. So 7 into 9 is 63. So this is another version of Fermat's relative theorem. Okay, in the first version, okay, if a p is a prime number, then a power p minus a is an integer multiple of p. Okay, a power p minus a is an integer multiple of p. Okay, in other version, okay, if a is not divisible by p, okay, if a is not divisible by p, then a power p minus 1 is an integer multiple of p. Okay, a power p minus 1 is an integer multiple of p. Okay, so that's what we stated here. So a power p minus 1 means a power p is a 2 power 6, 64. 64 minus 1 will be 63. Okay, so 63 is a multiple of 7. Okay, so we stated that it is equal. Okay, so this is another version of Fermat's relative theorem. Okay, so when you are going to the Euler's theorem or Fermat's theorem, okay, so what is the main objective of both the theorem is used to easily reduce the large power of modulo n. Okay, in both theorem may be used to easily reduce large powers modulo n. Okay, whether it's a Fermat's theorem or Euler's theorem. Okay, when you are going to the Fermat's theorem, it does not publish his proof for his theorem. Okay, the Fermat does not publish his proof for his theorem, but for the same theorem, the Euler's published the proof in 1763. Okay, in 1760 or 1736 or 1736. Okay, so in both the theorem, what objective of both the theorem is reduce the large power modulo n. So that's the main objective of both the theorem. Okay, so this is the proof for the Fermat's theorem. Okay, so you just consider if p is a prime and a is a positive integer, if p is a prime and a is a positive integer not divisible by p, then a power p minus 1 is congruent to 1 mod p. Okay, a power p minus 1 congruent to 1 mod p, where a and p should be a co-prime, a and p should be a co-prime, and a power p minus 1 should be multiple of p. Okay, so here its proof is consider the set of integer less than p. Okay, consider the set of integer less than p, 1 to p minus 1. Okay, 1 to p minus 1. Then multiply each by a and modulo p. Okay, multiply the integer with the a and modulo p. Okay, so that a, so when we are multiplying the 1 with the a and modulo p, we are getting the a mod p, 2a mod p, up to p minus 1 a mod p. Okay, they are multiplying the each by a and modulo p. Okay, here no two integers are equal in x. Okay, here no two integers are equal in x. Assume j into a equal congruent to k into a mod p, where j is lesser than 1, lesser than equal to 1 and greater than k, and k is lesser than j and greater than equal to p minus 1. Okay, since a is relatively prime to p, and eliminate a on both the sides. Okay, when you eliminate a on both the sides, we are getting this j congruent to k mod p. Okay, which is impossible because j and k are both positive integer less than p. Okay, j and k are both positive integers and less than p. Okay, so that we have to conclude x consists of the set of integers 1 to p minus 1 in some order. Okay, so consider x consists of set of integers 1 to p minus 1 in same order. Okay, so that we have to multiply the number in both the sides and taking the result mod p else. Okay, so we are multiplying both the sides, a into 2a p minus 1 into 1 to p minus 1 mod p. So this side we are multiplying a and p minus 1. This side we are multiplying with the mod p. Okay, so then a power p minus 1 factorial congruent to p minus 1 factorial mod p. Okay, so when we are cancelling both p minus 1 factorial, we are getting a power p minus 1 congruent to 1 mod. Okay, we are getting a power p minus 1 congruent to 1 mod. So this is the first version. In another version, okay, we are getting a power p congruent to a mod. Okay, where a power, as we said, where a power p minus a should be multiple of p. Okay, this is another version. Okay, so this is what the Fermat's theorem. Okay, in the Fermat's theorem, okay, so this is we have two version, a power p congruent to a mod p. Okay, and here a power p minus a. If p is a prime, again if p is a prime and a and p must be the co-prime. P is a prime number and a and p should be the co-prime. Okay, if a and p is co-prime, then a power p minus a is an integer multiple of p. A power p minus a is an integer multiple of p. In another version, okay, if a is not divisible by p or p is not divisible by a, then a power p minus 1 is an integer multiple of p. Okay, so this is the two version of Fermat's theorem. So whether it's a Fermat's theorem or Euler's theorem, the objective of both the theorem is to reduce the large powers modulo n. To reduce the large powers modulo n. Okay, the both objective of both the Fermat's and Euler's theorem. Okay, so next we with some example. Okay, so as we said, we are going to prove the Fermat's theorem here. So we are taking the a power a equal to 7 and p equal to 90. A equal to 7 and p equal to 90. Okay. So when you are applying this into this Euler's theorem, in the Fermat's theorem, okay, first we have to check p is a prime number. Okay, whether p is a prime number or not. Okay. Okay, and a is the a and p should be relatively prime. P is a prime number and a and p should be relatively prime. Co-prime. Okay, so when you are taking the GCD of 7, 19, it should be 1. GCD of 7, 19 should be 1. That's a co-prime or relatively prime we are saying. Okay, if it is 1, then we are applying this value into this Fermat's theorem. So a power p minus 1 congruent to 1 mod p. Here, a is a 7. So 7 power p, what is the p value here? 19. So 19 minus 1 congruent to 1 mod 19. What is the 7 power 19 minus 1? 7 power 18. So it's 7 power 18 mod 19. When you are taking the 7 power 18 mod 19, it always yield the result as 1. Okay. When you are taking the 7 power 18 mod 19, it always yield the result as 1. Okay. We can simply write it. Okay. You can simply write it. You don't need to perform any calculation. Okay. When if it is true, okay. If it both are if p is a prime number and GCD of a comma p is co-prime, okay, then you can directly apply here. When you are applying here, 7 power 18 mod 19 will always yield the result as 1. Okay, it always yield the result as 1. So we are proving this using the model exponentials. Okay, we are proving this value. Okay, using the model exponentials. Okay, so how we are proving this value? So here we are need to calculate for the 7 power 18. Okay, so using the model expansion, what I am dividing as 7 power 18 as a 7 power 8, 7 power 4. Okay, 7 power 4, 7 power 2, 7 power 2, 7 power 2. Okay, I am converting this man. Okay, when I adding 8 plus 4 plus 2 plus 2 plus 2. Okay, when I am taking this, I am get the value as 18. Okay, I am get the value as 18. Okay, I am dividing in this manner. Okay, so next, so why I am doing this? Okay, so when I'm calculating 7 power 2, I can calculate 7 power 4. After I am calculating 7 power 4, I can calculate 7 power 8. Okay. So in this way, I can able to calculate. Okay. So what is the 7 power 8 value? You can calculate what is the 2 power 18 value. What is the 2 power 18 value? 2 power 7, 128, 2 power 8, 256. Okay. So when you calculate 2 power 7, okay, 2 power 7 is a 128, right? Okay. In this way, we can move on normal way. Okay. So I will tell you this way, another way this for calculating the model value later. Okay. So just take in this way, we can split up the 18 as a 8 plus 4 plus 2 plus 2 plus 2. Okay. Now I'm going to calculate the value. So 7 power 0 and 7 power 2 power 0, 1, mod 19 will be always 7. Okay. 7 power 2 power 0, mod 19 will always yield the result as 7. Okay. Next is 7 power 2 power 1. When I'm taking 7 power 2 power 1 mod 19, okay. So it will be 7 square mod 19, 49 mod 19 will be always yield the result as 11. Okay. Next 7 power 4. Okay. When I calculate 7 power 4, I already know the 7 square value. What is 7 square value will be 11. Okay. So 7 power 2 power 2. Okay. So I'm applying the 7 square value here directly. So 11 square mod 19 value 121 mod 19 will be 7. Next I'm calculating the 7 power 8 value. So 7 power 4 whole power 2. Okay, instead of 7 power 8, I'm writing in this way. So I already know the 7 power 4 value. So I am directly applying the 7 power 4 value here. So 7 square mod 19. So 49 mod 19, 11. So now I know the value of 7 power 8, 7 power 4, 7 power 2 value. So I'm directly applying the value here. Okay, 11 into 7 into 11 into 11. This is not necessary. You can write only in this way. You can also write as 8. You can also 8 plus 4 plus 4 plus Okay, 8 plus 4, 12, 12 plus 4, 16 plus 2. Okay, so whatever the convenient way, okay, you can be able to write. Okay, for your convenience, you can write in any way. Okay, so or you can also write in the 8 plus 2. You can write in that way. Okay, so it is depend upon your convenience. Okay, you can split up in any ways. Okay, but should be in even numbers, not in odd numbers. Must be in even numbers. Okay, so like a 2, 4, 8, 16. So in that way only you have to convert the split up the values. Okay, 2, 4, 8, 16. Then you have having the 32. Okay, in that way only you have to convert. Okay, so I'm just in taking this way. So after multiplying and taking the mod 19 value, you can get the values remainder as. Okay, so we are proving that 7 power 8 mod 19 will always yield the result as. Okay, so using the model exponential, we are just proving. Okay, so we have already proved. So 7 power 18 mod 19 will always yield the result as 1. So we using a model exponentials, we are proving that. Okay, so in the model exponential, okay, we are converting the 18 exponent 18 as here. Okay, 18 plus 8 plus 4 plus 2 plus 2 in this way, or for your convenient you can write in any way. 8 plus 8 plus 2 or 8 plus 4 plus 4 plus 2. So for your convenience you can write in any form. Okay, then you have to find out the value for 7 power 2 mod 19, 7 power 4 mod 19, 7 power 8 mod 19. Okay, so you have to find out the value for this. Then you have to apply those values in the uh, uh, that powers. Okay, then you have, when you're taking the modulo, you can get the values 1. Okay, then if when you're getting the 1, we are proved that 7 for 18 mod 19 will always give the result as 1. Okay, this just proving that Fermat's theorem. Okay, next one. So we are doing the 6 power 10 mod 11. Okay, so we are finding the result of 6 power 10 mod 11 using the Fermat's theorem. Okay, as I have told, here A is a 6. Okay, A is a 6 and P is a 11. So what you have first, you have to consider, we are taking the any one of the Fermat's theorem. Okay, A power P minus 1 conjugate to 1 mod P, or A power P conjugate to A mod P. You can take any one of the version of the Fermat's theorem. After taking that, you have to find out whether P is a prime number or not. Okay, if the P is a prime number and GCD of A comma N, J comma P. If GCD of A comma P is a 1, I mean that means if GCD of A comma P is a co-prime or relatively prime, you can directly apply the first version. Okay, you can directly apply the first version. Okay, then A power P minus, what is P? 11. A power 11 minus A power 11 minus 1, that means 6 power 10. Okay, 6 power 10 will always yield the result as 1. Okay, 6 power 10 will always yield the result as 1. Okay, so we are calculating for the 10 only. Okay, 6 power 10. Okay, so you can directly result. This is the result. 6 power 10 mod 11 will give the result as 1 directly. Okay, so here we got the value 10. We need to find out the exponent for the 10. So we can directly find the value for the 10. Suppose you need a different exponent value. For example, here 3 power 12 mod 11. So you need to find out the result for the 3 power 12 mod 11. Okay, so when you are applying this value to the any one of the Fermat's theorem, here A value is 3, P value is 11. Okay, so if the both are co-prime, okay, then we can apply. Okay, so 3 power 12, 11 minus 1, 3 power 11 minus 3 power 10 mod 11 will always yield the result as 1. Okay, so as we know, 3 power 10 mod 11 will always yield the result as 1. Okay, but here we need to find out the result for the exponent 12. Here the exponent is only 10. Okay, the 3 power 10 mod 11 will yield the result as 1, but we need to find out the exponent for the 12. So what we are doing means, for 3 power 12 mod 11, okay, we are writing 3 power 10. Okay, for example here. So 3 power 10 mod 11. Okay, so it is different. Okay, so 3 power 11. Okay, mod 11. So what we are doing means we are taking the second version. Okay, so we are getting different values. So we are taking the second version. What is second version? A power P conjugate to A mod P. Okay, A power P conjugate to A mod P. Okay, so what is if A is not divisible by P? So 11 is not divisible by P. Okay, then 3 power 11 mod 11 will always yield the result as 3. Okay, 3 power 11 mod 11 will always yield the result as 3. Okay, so we are dividing this exponent, this value as a 3 power 11 mod 11 into 3 mod 11. Okay, 3 power 11 mod 11 into 3 mod 11. So the 11 plus 1 will be 12. Okay, so 3 power 11 mod 11, 3 mod 11. Okay, so that what we are getting value, so 3 power 11 is converting as a 3. So how we are getting the value 3 power 11 when you are applying the first second theorem. Okay, so we are getting 3 power 11 mod 11 we always yield the result as 3. So we are directly applying the 3 power 11 mod 11 will be 3. Next 3 mod 11 will yield the result as 3. So when you are converting multiplying this 9 mod 11 will always yield the result as 9. Even in the first version 3 power 10 mod 11 will be 3. So 3 power 10 mod 11 into 3 square mod 11. Even if you are doing it with the first version, you will get the result as 9. Okay, if you are taking first version or second version. So if you are taking the first version, we are having the exponent for the only 3 power 10. So you have to add for the 3 square mod 11 again. So 10 plus 2 will be 12. Okay, so when you are adding this, you will get the result as 9. Or if you are choosing the second version, okay, so you are getting 3 power 11 mod 11 into 3 mod 11. So 3 power 11 mod 11 will always yield the result as 3. So 3 mod 11 will be 3. So 9, when you are multiplying 9 mod 11, you will yield the result as 9. Okay, so when you are taking the both version, you will always get the same result. So result for the 3 power 12 mod 11 will be 9. Okay, this for the if you are having the different exponent. Are you clear with this? The same way we are performing here. Okay, 23 power 1002 mod 41. Okay, 23 power 1002 mod 11 mod 41. Okay, so again we are checking 23 41 will be the co-prime. If it is a co-prime, we are applying the first version. Okay, a power p minus 1 convert to 1 mod p. That means 23 power 41 minus 1. I mean 23 power 40 mod 41 will always yield the result as 1. 23 power 40 mod 41 will always yield the result as 1. So, but here exponent is 1002. So we have to find out the exponent as a multiple of 40. Okay, 1002 is converted as a 250 into 40 plus 2. Okay, so as we know, 23 per 40 will be 1. Okay, so we always have the convert the 1002 as a multiple of 40. Okay, so when you are converting a multiple of 40 as a 1002, 250 into 40 plus 2. 250 into 40 will be 1000 plus 2, 1002. Okay, so when you are writing in this way, 23 power 40 into 250 into 23 square mod 41. Okay, so 23 power 40 we always know it will be result as 1. So 1 power 250 into 23 square mod 41. Okay, 1 power 250 always will the result as 1. Okay, and 23 square will be 529. 529 mod 41 will be 37 mod 41. So always it will give the result will be 23 power 1002 mod 41 result is 37. Okay, so in this way you can able to calculate the result of the 23 power 1002 mod 41. So as I said before, Fermat's theorem or Euler's theorem, okay, the objective of the both the theorem is to easily reduce large powers modulo n. Okay, it easily reduce large power modulo n. Okay, that is the objective of both the Fermat and Euler's theorem. Okay, so when you are calculating this, if they not specify anything, you can apply Fermat's theorem or Euler's theorem. You can apply both the theorems, any one of the theorems. Okay, if they not specifically specify. Okay, for example, if they calculate using Fermat's theorem or calculate using Euler's theorem, means whatever they specify, you have to calculate using that specific one. If they not specify, you can apply anything. Okay, Fermat's theorem or Euler's theorem. Okay, so this is what the Fermat's theorem. Yeah, anyone have doubt in the Fermat's theorem? Anyone have doubt? Don't have doubts.